Okay then, section 10, so we're going to do sections 10.1, 10.2, 10.3, and 11.3 are going to be the ones that we do the rest of the semester. And then your test will be over chapters 10 and 11, and then we will have this couple days to study for the final, and then you'll have your final. Have I talked to you guys about how to calculate your grades yet? Well, okay, have I told you guys how to figure out what you need on the last test and on the final yet? Okay. Let me talk about it again. All right then. Chapter 10 then. First of all, just kind of previewing where we're going. In this chapter, we introduce methods for determining whether a correlation or an association between two variables exists and whether that correlation is linear. For linear correlations, we can identify an equation that best fits the data, and we can use that equation to predict the value of one variable given the value of the other variable. So trying to look at data that's coming in and seeing if there is a linear association between those. So we're looking at paired data when we do this. So this section, looking for what that linear correlation R is. This section introduces the linear correlation R, which is a numerical measure of the strength of the relationship between two variables representing quantitative data. Using paired sample data, sometimes called bivariate data, we can find the value of R. Then we use that value to conclude that there is or is not a linear correlation between the two variables. If you have had college algebra, you've already worked with a linear correlation. So when you're looking at taking paired data, so it's got to be quantitative data. Quantitative means it's a quantity, it's a number. So you're taking numerical data and trying to see if there's any kind of relationship between those. So if I was to take your grade on the last test and your height and try to see is there a correlation between those two things. Did taller people do better? Did shorter people do better? Is there a relationship between those two things? So trying to see if there's a relationship between that. Or if, on the other hand, if I tried to look at, and this is one that I do frequently, is look at is there a relationship between somebody's grade on their homework compared to their overall grade in the class. Then there's usually a linear correlation, that usually those people that spend more time doing their homework and do better on their homework tend to also be those people that do better on their tests and have a better overall grade in the class. And so looking to see is there that kind of correlation, that kind of relationship between paired data. But it has to be things that are numerical to be able to look at it. So a correlation exists between two variables when the values of one are somehow associated with the values of the other in some way. Just because there's an association doesn't mean that one causes the other. You're just looking at the fact that there is some sort of relationship between those two things. An example. Is there a relationship between the number of hours a person studies for a test and the grade on the test? What would you guys expect? Okay. I would expect there to be a positive correlation, that I would expect that somebody that spends more time studying should hopefully do better on the test. If you spend less time studying, it's anticipated that you won't do as well on the test. So you anticipate that there is a relationship between those. It doesn't mean that just because you study for 3 hours that you're guaranteed to get an A on the test. It just means that if you studied for 3 hours, it's anticipated that your score should be better than had you only studied for 45 minutes. There should be that sort of relationship between them. How about, is there a relationship between the money in your pocket and your height? I don't anticipate there to be any kind of relationship between that. I don't anticipate there to be a relationship between your height and how well you did on that last test. I do anticipate that there is a relationship between your homework average and your class average. That those people that have spent more time working on their homework probably have a higher class average than those people that haven't turned in as much homework. So I anticipate that there's a relationship between those two things. So as we explore the data, we can often see a relationship between two variables by constructing a scatter plot. We did scatter plots back in chapter 2. That's when we looked at plotting all of our different points. So when you had your paired data and we just went through and plotted each of these different points, that was an example of what we had as we were looking at things. So these were each of our different sample data that we had. Well, now as I look at this one, it looks like there is a trend that it kind of looks like, oops, not really the best fit line there because it went up a little too high. Looks like there's this kind of relationship that it looks like it's increasing as I go from left to right. Well, if it has that tendency to increase as you're going from left to right in this linear pattern, then this one has a positive correlation. Because this best fit line, this line that goes, it might still not be the best of the best fit lines, but this line that kind of goes through the middle of all those has a positive slope, so it's a positive correlation. So there's this relationship between these. Versus this one tends to have a negative correlation. It seems to be going down as I go from left to right. And so since it has a negative slope, it has a negative correlation. Now, both of these have got this R value underneath it, and we're going to look at how to find R in just a little bit. That R is my correlation coefficient. It tells me how good my relationship is between things. The closer my correlation coefficient is to either 1 or -1, tells me how good that relationship is. So if you look at the absolute value of these values, 0.965 is closer to 1 than 0.85 is. Therefore, this one has more correlation. It's better correlated. And you can see that in the graph. You can see that all these points are closer to each other and fit that pattern better than what these do. Even though we can see in both of them there is a relationship between them, the relationship in this one is a stronger relationship than this one. So it has a value closer to the absolute. Its correlation coefficient, its R value is closer to the absolute value of 1. Now this guy, does it look like it has a correlation? This one just looks like I threw a bunch of points at the board and they just landed where they landed. There's not any kind of relationship between them. It has no correlation. In this case, its correlation coefficient is 0. 0 is saying there is absolutely no relationship between them, that the best predictor could be a nice horizontal line, could be the vertical line, could have a positive slope, could have a negative slope. There is no way to use anything to predict what's going to happen. Now, most of the time we don't come out with a correlation coefficient being exactly 0, meaning there is absolutely no correlation between two things. But if it's a correlation close to 0, then that's really telling me it doesn't have any kind of relationship between those things. Now, what about this one? Okay, there I'm saying it looks more like a parabola. There's not a nice linear correlation, but it looks like it's got a nice quadratic relationship between it. We're looking for linear correlation. This guy doesn't have a linear correlation. There's not a good line to use, because if I had one straight line over here with a positive slope, it'd be great for the beginning, but it totally loses the end. And so there's not one nice straight line that fits it. If it's looking for something that has a quadratic relationship, this one has a nonlinear relationship. My correlation coefficient, R, is a -0.087. It's very close to 0. There's not a good linear correlation, which is the reason why it's very important that as you do these, we still graph our data. Because if I looked at this and said, well, my correlation coefficient looks like it's 0, there's no, and that tells me there's not a linear correlation, but to recognize that there does look like there's something that's not a linear correlation. Or there will be times that you might have something that has this nonlinear relationship, but depending on the points you pick, it may have some sort of, I don't know, line that kind of comes through here, and that might have a correlation coefficient that's an R value that's a 0.8 or 0.7, where it sounds like it might have a correlation, but when you look at the data, you realize, yeah, that line in the middle doesn't really look good. So we have to graph our data to be able to see what's going on as we're doing things. Now, if we're going to look for our correlation coefficient, the requirements we have to have. First of all, the sample of paired data is a simple random sample of quantitative data. So it has to be paired, so it's going to be points that are x, y. If you're going to graph them, they have to be quantitative, they have to be values, they have to be numerical values. It needs to come from a good, simple, random sample. Sounds like everything else that we've done so far. A visual examination of the scatter plot must confirm that the points approximate a straight line pattern. So if you graph them and you see that it looks like a parabola will fit them better, then you can just stop there and say it's not going to have a good linear relationship. And so making sure that we can look at them and look like they have some sort of relationship, Or if you looked at that one that just looked like I threw points at the board, then you can tell from that one it doesn't have a good linear relationship. The outliers must be removed if they are known to be errors. The effects of any outliers should be considered by calculating R with and without the outliers included. Those outliers, those extreme points, can really have a strong impact on our data. And I forgot what the name of those are. When they're an outlier and they're on the extremes, they've got a special name, and I've forgotten what that is. But we have to look at it with and without those outliers, because if we're trying to figure out, and what we'll be doing, first of all, is seeing is there a correlation, and then figuring out what's the equation for that best line. The equation is going to be in section 3. But as we're looking at trying to use those and figure them out, if you have a point that's, if all my other points are way over here, and then I have one more point that's way up here, this one point, because it's so extreme outside, such an extreme outlier, does a lot to pull up my values. So that one point might make all of my graph kind of go above every other point. So we have to look at what's going on with and without that outlier. Now, if I know it's a bad point, if you know it's absolutely impossible, we had one problem on our extended problems where we changed somebody's age from like 84 to 840 or something. Maybe it was 54 to 540. Well, obviously, somebody that's 540 years old is a definite incorrect data value. 540 years old, that would be our outlier that would be way beyond the scope of everything else. If it's known to be wrong, we have to throw it out. But if we were looking at ages and everybody else is in this age range from 18 to 25, and then we had some 60-year-old in here, well, a 60-year-old is possible. It may not be the normal of what you see on college, but it's possible to have a 60-year-old on campus. And so that one would still be an outlier because their age is extremely more than the typical range that we had of people. And so that outlier needs to be considered what's going on with and without that. Because having that one person in my sample that's 60-year-old and has whatever, maybe it's an age in the GPA comparison. That one person with that GPA, well, if it's an extremely bright 60-year-old or an extremely not doing so hot 60-year-old, can really impact what's going on the graph as you're doing things. All right, so now the notation for our linear correlation coefficient. We are still using n for the number of pairs of sample data now. So we're still looking at the number of sample data, but they're ordered pairs because you're taking both of those points together. This is telling me the sum. You're adding all those values together. So this is your sigmas to adding everything that comes afterwards. So this is saying the sum of my x's. So you're adding all the x values together. This is saying the sum of my x squares. So you're squaring your x's first and then adding them, which is different than the quantity, the sum of x, the whole quantity being squared, where I've already added all my x's first and then I'm squaring that answer. So your order of operations matters. Do I square everything first and then add them? Or do I add everything first and then square it? So pay attention to your notation as you're doing these. Questions on any of that? Sum of xy's means you're going to multiply your x and y's together first and add all of those. R is your linear correlation coefficient for your sample data. Rho is your linear correlation coefficient for the population. So this is the Greek letter rho. Looks very similar to P, just a little bit more scripty looking, I guess would be a way to say it. So this is rho versus R is your linear is for your sample. Most of the time we're going to be looking at sample data. Occasionally, though, if you're going to have your population, if you had everything, every single value. So if I was talking about statistics grades, then you guys are the entire population for this semester. And so I could look at what's going on with your specific grades compared to maybe if I wanted to look at grades compared to height, the whole entire population would be in my values that I'd be looking at, versus if I just used you guys as a sample of NCMC students, not my good simple random sample, but if I used you as a sample, then that would be looking for R as my correlation coefficient. Questions? it didn't have the y's, the sum of the y squared versus the sum of y, quantity squared, same thing. That would just be looking for your adding your y values. If we're looking at doing these, this is where we're going to go back to, similar to when we were trying to figure out, what did we do first? Oh, standard deviation, when we had lots of steps and we had to do the different columns when we did the standard deviation. When we go to do the correlation coefficient by hand, we're going to have multiple columns that we will do things, where this is adding the entire column of all the x's. This one here, we are going to have a separate column where we square all the x's first and add that entire column. Versus here, we will already have added all the x's, which was back here, and you just take that answer and square it. So your order of operations being different. Versus this one, again, I'll have to have another column where I multiply my x's and y's, and I'll add that entire column. This is my formula. Again, this is not one that I will have you memorize. This is one, though, that I'm going to make you do by hand, because I do want you to be able to make sure you can follow the order of operations as you do some of these. We will eventually look at the calculator shortcut on them also. But you'll have to, I think on the test even, I make you do one by hand. I need to double check that, but I'm 90% sure on the test I make you do one of these by hand. The formula is on your little reference sheet also. So I find where it's at again. So on that second page, you had the chapter 8 stuff. Chapter 9 comes after it. Then it goes to 11, and then over here is chapter 10. Chapter 10's got a line that kind of goes down through the middle of it. But we're looking at finding our correlation coefficient R. And so we'll be following, going through, doing our correlation coefficient. It is one of those. Yeah. So if we look at doing this, I don't remember what this data stood for. Number 10, I guess, from page 531. If we look at what it stands for, it still doesn't tell me. This is just what it gives me. So if I'm trying to look to see, is this paired data, what is that correlation coefficient R? So first of all, we need to go through and find the number of my sample times the sum of x, y. So I'm going to have to find what the product of x times y is going to be. I'm going to take the sum of the x's, the sum of the y's. Here I'm going to do the sum of the x squareds and take that times n. So I've got to do another column for my x squareds, and I'll add that entire column. Versus this is going to add all the x's, so we'll have to add all of the x's together. Same thing goes over here, so you're going to need your y squareds. Do what? Do I do all that for you on the next slide? I really wanted to make you guys do it by hand, though. But we'll just skip to the next slide. So I'll go ahead and do all that for you. So now this is doing my x squared. So I took the 10 squared, the 8 squared to get all these numbers here. This is my y squared. So I took my y column and I squared each value to get those. This is the product of x and y, so the 10 times the 7.46 to get here. So going through doing all of those. I want you guys to plug it into the formula, though. So find the right numbers to plug into each place. Just go ahead and use the numbers that are there. Just put down here, you just put the bottom numbers. Go ahead and just put your X, Y's and put these bottom numbers. That way you can figure out what goes where. Oh, you already did the X, Y's. And to help you out the notes later too, go ahead and put what your X and Y's add up to at the bottom, because you'll use that. Did you get the numbers yet? Okay. Don't worry about putting them in your calculator yet. Just use the bottom numbers that I've got there and plug them into things. So I've already added up each of these different columns for you. Don't worry about erasing what you've done, because you're probably on the first few steps that we'll do here in a little bit. Oh. Yep, I've already got the adding each of these columns together for you. So what is n? Okay, n is going to be your 11. What is the sum of my x, y's? Did it just go away? Did. That's really odd. What's the sum of my x, y's? Once you have an answer, let me know so I can come over and check and see if what you've put in the calculator looks right. Questions on where I'm pulling anything from? If you add up all the points, there's 11 points. I had 11 points to start with. So these were my original ordered pairs. So we had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 points. Yeah, let me know when you get it so I can see if it looks right. No. The reason is when you divide it, you're just dividing by this square root, and your answer is going to be times the next square root. You need a parenthesis after the division. I'm not sure with having it take the answer from before if it'll be okay or not. When you divide, it's just divided by this first square root, and then afterwards it is subtracting the next square root. So you want to have it multiply the next square root. So you're going to need to have a parenthesis after this dividing. You need to have a parenthesis there. Oops, I just did that in the wrong order. That way it's dividing the whole quantity, and that should be a times.
Do I need one up and down here too?
I'm not as picky. The calculator doesn't care about that. Yeah, it does care about something I just did though. Come check on that one in just a second. Now part of the problem. We also need a parenthesis on the top. Oh, are you doing the entire numerator? Okay. There's what the other problem is. You need a parenthesis after you square this because you're just taking the square root of all of that.
Mm-hmm.
And so
Okay.
we need another parenthesis here because you're just taking the square root. You're going to close that parenthesis.
Okay.
This parenthesis here, it doesn't care if you take this, if you close it, but the one that you're taking the square root of, you did. There we go. Now you're good. You're not good. That's the problem. Okay. Let's just square him. You need another parenthesis right there. Okay. Now you're good.
So I can add something without it introducing the next
Second and insert.
insert.
Yeah.
I don't know what I'm doing wrong here.
You need a parenthesis closing the square root. I'm not sure if it's going to, I'm going to change this up here to be 604.97 because I don't think it'll like it otherwise. And so we needed to insert parenthesis there. That way we're just taking the square root of all that. Something's still not right. Oh, and that guy there needed to be squared. So square him and you should be good. Yep. You're breaking it into pieces, and so I can't check it real quick to see where your problem is coming from. Number there's not right. And there's a squared on the 82.5. Yeah. Okay, that would be the problem. Okay, now, as you guys can see, doing this by hand is a royal pain. But what it is telling me is it's really looking at if I was trying to find the difference between things. Really what it's trying to see is how far away is each point from where the average of all those points would really be looking for is what it's talking about. If you were to try to find, well, all those x's, how far away is my x from where it kind of should be, where it would look like if you're looking at those. And so it's, and where are the product of those two things. How far away are they? So it's telling me if we were to have a line going through it, how far away is all of these different points really looking at? And so it's got to take both into consideration, both the x values and the y values. And so that's the reason why this one goes through having so many steps involved. So if you've got very many points, or in this case, our points aren't very friendly points, being able to look at doing it with the calculator and letting it calculate it out, much, much easier. If you have already done, if you've already been in college algebra, then you had the same calculator, this first step you've already done, and it's something you only have to do once, which is to turn your diagnostics on. So if you've already done that, great. If not, turn it on again. It's not going to hurt it if you're not sure. So to be able to turn your diagnostics on, the first thing we have to do is, it's not in a really convenient place. You go to second and number 0, because that's your catalog, and it's just going to start listing all the things. Well, we need to go to diagnostics. You can either arrow down till you get there, or if you hit alpha and D, which D is above the x to the negative first, for some reason it makes you do it twice before it goes to the D's. Then you can arrow down until you get to the diagnostics on. Is everybody there? Once you're there, hit enter, and it's asking, is that really what you want to do? Hit enter again, and it's done. The diagnostics are now on. What that's going to do is make it to where the calculator is going to tell you your correlation coefficient every time. Otherwise, when we went to calculate it out, it wasn't going to tell it to me. Has everybody got that on? So now what we want to do, to find our correlation coefficient, we're going to put our data into list 1 and list 2. And we're going to calculate out the linear regression. So first of all, go ahead and put this data in as list 1 and list 2. So to put it in, remember it's stat and edit. Arrow over up to the top and clear out anything that's already there, and then just put your data in there. Okay, does everybody have their data in? So now that I have it in as list 1 and list 2, I've got my paired data. What I want to do next then is to find my linear regression. We're going to go to stat, arrow over to calculate, and it's this fourth one down, the linear regression ax plus b, because I'm trying to figure out what is my linear regression correlation coefficient. And so if you hit enter, then it's asking where is it coming from. If it's in list 1 and list 2, you can just hit enter again. If you put it somewhere else, then you can put, if you put it in list 3 and list 4, you can do L3, L4. So it's just asking where it's at. And now this last number it gives me is my R, is my correlation coefficient. That's the same number we just came up with a little bit ago, which is that 0.816. And most of the time we round the correlation coefficient to 3 decimals, or 3 significant digits. I think so. I'm not even sure I've got that listed anywhere on there. Only when I tell you to do it by hand. And I will make you do one of them where you get to do it by hand. It won't have as many points as what we just did. Now, when we've been doing this one, I was saying we need to look at a visual idea to see if it even looks like it's linear. We're saying our correlation coefficient is 0.816, which is somewhat close to 1, but it's not awesome, but it's not horrible. And we'll look in just a second at how to decide if it's good enough or not. But I also want to look at what's the graph look like to see if the graph even looks like it should be a linear correlation between these. Because it is a positive number, that is telling me it would have a positive slope, that there is a positive correlation. So to see what the graph looks like, we will go to second and stat plot. We are going to turn that first plot on. It's asking what type of plot. Well, I want it to be where I'm connecting, or I'm just looking at the point, so it's a dot plot. X list is, I put the X's in list 1, I put the Y's in list 2, and then what kind of marks we want. Either use the boxes or the plus signs because the little dots are kind of hard to see. Now, we're wanting to go ahead and do zoom stat because we want to see the points that we had plotted. So if you go to zoom, and we're going to go down to, I don't remember which number, number 9 gives me zoom stat. That way it sees those. I will have my points within the graph that I'm looking for. I used squares. You can either use the squares or the plus signs. Don't use the little dots because they're harder to see. From this, what do we notice? We definitely have an outlier. Everything else looks like it fits a nice linear pattern really, really well, but we have this one point that's way higher than where it looks like it should be. This is one of those where, because this is definitely an outlier, it says let's go back and look at that point a little closer and see if it's really accurate. Maybe we have a typo, but obviously since we all have the same point, that we didn't just have a typo. Maybe the book has a typo. Maybe it was that we were each going through and maybe, oh, I know one that I see frequently done for this linear correlation is you're comparing your height compared to your wingspan. Wingspan being if I stood and stretched my arms out as far as I could. Well, people that are taller have a bigger wingspan than people that are shorter because usually you're pretty proportional. Usually your wingspan is very close to what your height is. And so if we were doing that and I had everybody in here measuring those and we have this nice positive correlation and we have one person way out here, chances are really high that this one person way out here messed up. And so we can look and say, well, it looks like, we'll pick on Aaron since he's not here, Aaron looks like he didn't measure very accurately, and we'd make him redo it and see if that really is accurate. Now, if Aaron really measured and we all watched him and he really has those right numbers, then it could really be that he's just not as proportional as everybody else. But if we remeasure it, we find out, yep, that was the wrong numbers and he should really be way down here, then it's another way of looking at stuff. And so it tells, when you're looking at these, it gives you an idea of where are those outliers, and you kind of have to look at things with and without those outliers involved. Questions? Now, how do I decide if it's good enough or not? Trying to figure out what the correlation, oh, and I just ran out of time, dang it. We'll look at finishing this next time, but I'm still going to make you do some homework. I want you to do, which ones? I know I want you to do number 13 by hand. Bless you. Actually, I think that maybe, probably just make that be the only one. You're going to have extra homework on Wednesday because we're going to do both 10-2 and 10-3 because we'll finish up 10-3 on Wednesday. I think it looks like we'll probably be able to have our test hopefully on the 27th and give us back our 3 days of being able to, our 3 days that we're wanting to do for study for the final. That's the words I'm looking for. I think I'm going to make you do number 13 because I really want to make sure that I have talked to you about what's good enough before I have you do very many of them. So just do number 13.